Okay, so thank you for coming. Let's hope that soon we will have face-to-face colloquiums too, as we used to. And today is really a pleasure to have Manuel Rivera from Purdue University. Manuel is a new generation of Latin mathematicians. He was in the math international Olympiads, and then he went to MIT for the undergrad, and he uh, convinced my oldest son actually to go there, and so they were classmates in some of the courses. Manuel continued with the academic careers. He went to City University of New York to got his PhD, and then he has been in the CNRS postdoctoral research, and also there was a joint position between University of Miami and CINESTAB in Mexico, and now he's assistant professor at Purdue. He is also one of the organizer of an incredible activity, which is the Ciber Colloquio Latinoamericano that has been running since last year, mathematics in Spanish, with a great success all over the Latin American people connect on Fridays. So, well, he's going to talk about higher structures in topology and algebra, and without anything else to add, there is Manuel.
Okay, thank you for the invitation, Wilfredo. Yeah, so that's a great story. I met Wilfredo's son in Greece. I was 15 or 14 at the time, and I went for a in Math Olympiad to Greece. I'm from Puerto Rico, and he was coming from Venezuela, and we kept in touch doing math. And I went to MIT, and he was in Venezuela at the time, and I was convincing him to come, and he applied, and we became friends. We learned math together, and then he continued to do computer science, and I stayed in topology. Actually, topology was like the breaking point for him. I remember he was a very good algebraist and very good in discrete math and number theory. And then at topology, we took a topology class together with Munkers, and after that, I think he decided to do computer science, and I decided to do topology. So that's a good story. Anyway, thank you for the invitation. I want to share a little bit with you about essentially the flavor of modern, a little bit of the flavor of modern algebraic topology. So yeah, so let me start stating the goals and the motivation for this talk. So often in mathematics, we find it useful to relax the notions of equality and isomorphism by some weaker equivalence relation, okay? This is not only seen in topology when you relax your notion of, say, homeomorphism for homotopy equivalence, right, which is weaker. We also see this in algebra. We also see this even in logic and computer science and even arithmetic in some sense, right? Like, I mean, I don't know if you've seen these debates on social media about if 1 + 2 = 3, what does that mean, or and so on. I think behind this kind of debates, of course, there's some like pseudo philosophical discussion regarding of what equality means, right? But behind all of these debates, you also have these higher structures in some sense. And let me kind of say something from this perspective. You know, first you have to make sense what 1 plus 2 means, right? And of course, if you're a computer scientist or if you're building arithmetic from the basics of set theory, this should mean something like that. But then you quickly realize that that expression is ambiguous, right? Because it could mean that or that, right? So you really want to think of maybe not equality here, right? Maybe we really want to think of here as a link between these two symbols in some sense, right? They're related. But then when you think of this as a link, as a relation, you quickly introduce other links that involve these associativity relations, right? For example, now you quickly have this new link. You can say, I don't know, 1 plus 2 minus 1 equals 3 plus 1 minus 1, right? And of course, I'm using this link here. I'm thinking of this as a link. And in some sense, this is a different link than that link, right? So you want to have some mathematical framework where you can keep track of all this structure in some sense. All of these links and links of this sort and these kind of relations of associativity and so on, right? You want to kind of preserve all of these structure in some framework. And in a sense, this is clearly seen in topology. And this is what I want to explain today, how this kind of links and links between links and links between links appear very naturally in topology. But they are also present in other aspects of mathematics and even philosophy, I would say. Okay, so again, it's useful to always be careful when we say two things are equal. Even be careful when we say two things are isomorphic. Of course, depending on the context, what does that mean? It's often useful to relax these notions by something weaker. Okay. So again, all the details or the mathematical content are in describing mathematically exactly how much we want to relax from a strict notion of equality or isomorphism to obtain a new suitable notion of equivalence, which is more flexible for certain purposes. Okay. And this procedure will involve keeping track of some form of higher structures, some hidden structure. For example, when I said 1 plus 2 equals 3 or 1 plus 2 is related to 3, there was some associativity relations hidden behind that and different ways of getting from this thing that we were calling 1 plus 2 to 3, right? So this is the kind of hidden structure that I'm talking about. And it will be very, very explicit in topology. Okay. So the goal of this talk is to discuss constructions and examples of what I'm calling higher structures, motivated by the following questions, which are central in my field of research, which is algebraic topology. So a central question that we try to answer is, what is the algebraic nature of space and continuous maps? Okay. Or more precisely, can we completely characterize topological spaces up to homotopy in terms of algebraic data? Okay. So is there a package of algebraic structure I can associate to geometric objects, or more precisely to a topological space, that completely determines that space up to this notion of homotopy? So you wear your homotopy glasses, right? Where like a donut is the same as a coffee cup, a cylinder is the same as a circle because you can squish your cylinder and so on, right? These are this is the homotopy equivalence relation. So if we're trying to capture the notion of shape using this equivalence relation, can this be made algebraic, completely algebraic? So that's a central question that we algebraic topologists try to answer, okay? And in trying to answer this question, we will see this kind of phenomena of what I'm calling higher structures. So topology is the study of those properties of space that are preserved under continuous transformations. And the main objects of study are topological spaces and continuous maps between them, right? And let me now give you an example of what I talked at the beginning of this, of weakening a notion of equality for something weaker, and why this could be useful in topology. So if X is a topological space and A and B are 2 points in a topological space, the notion of equality, 2 points are equal, may be weakened to there is a path between A and B. The points are connected by a path. So maybe your topological space, maybe you have some holes like that, right? So maybe we can declare 2 points to be related, maybe A and B, if they are connected by a path, if there exists a path. So for example, in this picture, A and B are related, but A and B are not related to C, right? So this seems something sensible to do if you want to understand the path components of your space, right? In other words, the set of equivalence classes under this notion of equivalence relation is actually the set of path connected components of your space, and it's denoted by this symbol pi0 of X, right? So it's just a set of connected components. And this 0 suggests that we might be able to go higher here, right? So instead of considering points, let's consider loops. Loops based at some point in your topological space. So let's do a picture here. So you suppose you have a topological space X, and suppose you have a point, a base point, which I'm going to call B. And now suppose alpha and beta are 2 continuous maps from the circle to X. So 2 loops, 2 loops, alpha and beta in X. So the notion of equality, calling these 2 maps from the circle to X to be equal, can be relaxed by homotopy, okay? Namely, if there's a continuous transformation, let me do another picture here. If you have 2 loops based at the same point, you can declare them to be related or homotopic if there's a continuous transformation between them. Namely, if there's a family of loops interpolating alpha and beta, right? So a family of loops, maybe let's use a color here, maybe a family of loops parameterized by the interval, say, okay? So at time t, maybe you have that red loop, and as t varies from 0 to 1, it interpolates between alpha and beta. So if there's such a family of continuously varying family, we call alpha and beta homotopic loops. And this is, of course, weaker than saying 2 loops are equal. And it's more flexible, but it leads to a very interesting invariant of spaces, which is known as the fundamental group, right? So far, I have just described a set, the set of homotopy classes of loops, but this set has a natural group structure. Namely, any two loops, alpha and beta, can be concatenated. You can do alpha first and then beta to obtain a new loop, right? You can consider that as a new loop. Of course, that involves some reparametrization of of the domain circle, right? Because now you're running the first loop through the first half of the circle, and then the second loop through the second half of the circle. Because you want to consider now this, maybe we can call alpha star beta, you want to consider that as a map from the circle to your space, right? So the idea is that you can concatenate loops. That gives you a group structure and associative multiplication. Running the loop in the opposite direction is the inverse operation. It gives you the inverse of a loop. And the constant loop, which stays at the base point all the time, gives you the identity. And this is a group structure on this set of homotopy classes of loops based at some base point B. And that's called the fundamental group of a space. Okay. Good. And as I said, you can probably guess that you can keep going higher, right? You may define higher versions of this fundamental group where you replace the circle by a n-dimensional sphere, right? So now the pi n of x, again, based at some point B in your space, is the set of homotopy classes of maps from the n sphere into X. So an element of this set is a homotopy class of maps, of base maps, right? It sends your preferred base point in the sphere to the base point B in X. And this also has a group structure, okay? There's a way of concatenating spheres inside a space as well, generalizing the concatenation of loops in the fundamental group. So given any space, I have described, or I have outlined, a way of associating a sequence of groups to that space. These are called the homotopy groups, okay? The 0th one is not a group, it's just a set. Remember, the set of path components on your space. Then pi 1 is called the fundamental group. In general, this is a non-commutative, a non-abelian group. And it turns out that after the fundamental group, the higher homotopy groups will always be abelian. That's like a little theorem you can prove, okay? And of course, I've used here the notion of homotopy between loops and between maps of spheres, but this notion of a homotopy can be defined for general continuous maps. I can make sense of what it means for two continuous maps between topological spaces to be continuous. More precisely, two maps, F and G, between topological spaces X and Y are called homotopic if there's a continuously varying family of continuous maps. Let's call that HT, parameterized by the interval, that interpolates between F and G, right? That it starts with F and ends with G. If such a family exists, of course, this is highly non-unique. I just care that a family like this exists. Then I say F and G are homotopic. Okay. And now I can define two spaces X and Y to be homotopy equivalent if there exists a pair of maps, F from X to Y and G from Y to X going the other way, such that each composition is homotopic to the identity, to the corresponding identity map. So if we think about it, we're relaxing the notion of homeomorphism by something weaker. You say two spaces are homeomorphic if there exist continuous maps F and G, which are strictly inverse to each other's. Namely, this is replaced by equality. That's homeomorphism, right? So in the notion of homotopy equivalent, I'm relaxing this notion by, I'm replacing equality here by homotopy of maps. Okay. And this is what homotopy, the notion that homotopy theorists work with. We consider two spaces to be the same, essentially, if they are homotopy equivalent. And this captures essential features of the shape of a geometric object. It can, in some sense, we use this as a definition of shape, if you think about it. Two objects have the same shape if they are homotopy equivalent. That's what shape means for a homotopy theorist. And as I said, this notion of homotopy equivalence, which I'm writing by this symbol, which is called, is this similarity or something, is weaker than homeomorphism, which I will denote by this congruence symbol. Okay. So a theorem, a classic theorem of algebraic topology, says that if X and Y are homotopy equivalent, that means in particular that there exists a map from X to Y and a map from Y to X, which are homotopy inverses to each other. Then these maps induce isomorphisms in homotopy groups. Okay. So homotopy groups are a homotopy invariant of your space. That's what this theorem is. Yeah.
Manuel, for any B and any C?
Yes, for C should be, sorry, C should be here. I could write F of B, right?
F of B, okay.
Yeah, for any B in X.
Can I ask a question?
Yep.
So on the conclusion of this, you're using the congruence symbol for isomorphism of these as groups, except for n equals 0, it's just an equality.
Exactly. For n equals 0 is an, bijection of sets, right? Yeah. Isomorphism of sets, which is a bijection. Yeah, exactly. Thank you for the comment. And another theorem of algebraic topology, maybe a counterexample in algebraic topology, is that there are examples of non-homotopy equivalent spaces X and Y with the same homotopy groups. In other words, these homotopy groups are useful to distinguish spaces, but they do not characterize completely the homotopy type of a space. Okay, so if I'm able to prove, if I have two spaces and if I'm able to prove that the homotopy groups are different, then I can conclude that the spaces are not homotopy equivalent. But if it happens that the homotopy groups are isomorphic, I cannot say much about my spaces. Okay. So a natural question, and this is a central question in algebraic topology, is if it's possible to characterize spaces up to homotopy equivalence by algebraic data. So if it's possible to produce an algebraic package so that you do have that if the algebraic objects are equivalent under some notion of equivalence, then the spaces were homotopy equivalent, right? This is what I mean by completely characterizing spaces up to homotopy equivalence. And surprisingly, after many years of research, the answer seems to be yes, under some conditions. And again, the idea is to try to encode algebraically the higher structures, higher algebraic structures hidden behind these homotopy groups. So in some sense, these homotopy groups are forgetting too much information. Okay, and I want to try to remember the information that they're forgetting in terms of algebraic data. And this is what I called higher structures. They're hidden behind these groups. And let me say, first of all, that this is a much more conceptual discussion. It's not a computable discussion. These are highly non-computable. First of all, the theory of groups, in some sense, is embedded here, and the theory of groups is known to be non-computable. For example, if you given a presentation of a group, there's no algorithm that will decide if that group is trivial or not. So this is highly non-computable, and these homotopy groups, which are kind of the tip of the iceberg behind these, at the top of these higher structures, are also already extremely hard to compute explicitly, even for spheres. The higher homotopy groups of spheres are known to be one of the hardest problems in algebraic topology. Compute them explicitly. They already encode a lot of information, but still we are able to formulate a mathematical statement that says that in some sense topology is determined by algebra, even if it's hard to compute and most of the time non-computable by algorithms. That's what I mean by non-computable. So I kind of want to give you an example of these higher structures today, as I said, and I'm going to start with describing the higher structure behind the fundamental group in some sense. And this piece of structure is already hard to describe mathematically. You will be amazed. Okay, so remember when we took when we defined the fundamental group, we took homotopy classes of loops, right? But let's maybe not do that, okay? And let's see what we have before taking homotopy classes, before modding out by the homotopy relation. If you think about when we were considering loops, there was already an interesting space that appeared, which is the space of based loops in a space X. So given a topological space X with a base point B, I can consider what we call omega B of X, the base loop space of X, which consists first as a set, is the set of all continuous maps from the interval or from the circle, right? Base maps from the circle or from the interval, which are continuous and send the starting point and end point to the base point B, right? I'm not taking a homotopy relation yet, and I don't want to do that because I sense that this might forget a lot of interesting information. So I'm considering this as a set. First, that's huge, right? It's a point in this set is a loop in your space. So you have all of these are elements in your set, right? And there's a topology, a natural topology in this set induced by the topology of X called the compact open topology, okay? It basically says that two loops are closed essentially if their points are closed in some sense in the underlying topological space. In any case, you can make this into a topological space in a natural way, okay? So there's a notion of closeness. In this space, a point is a loop in X, okay? Furthermore, concatenation of loops. Remember, we used concatenation of loops to define a group structure on the fundamental group. That induces a continuous product on this topological space of based loops. Okay, so it's a continuous map, this concatenation of loops. Given two loops, alpha and beta, you can concatenate them to obtain a new loop. And let me stop here and say something, because there's a subtlety that I mentioned earlier. When you concatenate, you want to consider alpha and beta maybe using this same notation, alpha and beta as a map, as a continuous map from the interval to x, right? Alpha was a continuous map from the interval to x, and beta was a continuous map from the interval to x as well. So in order to make sense of this, there's a choice, right? I have to reparameterize my loops alpha and beta, right? So there's if you want to be democratic, there's a way of doing this in the most democratic way. You can choose the base point, right? And you can run alpha on the first half and then run beta on the second half, right? And then you get a map from the interval to x. You cook up a map from the interval to x using alpha and beta, right? But of course, you could use any other point inside the interval, be greater than 0, smaller than 1, right? And it will give you a different loop, but it will be related to one defined using a different choice, right? It will be related by a homotopy, in fact. Okay, so there's a choice when I define this concatenation product. So for the rest of the talk, I'm assuming that choice will be 1/2, okay? So it turns out, because of this choice, that this product is not associative. If you compare, for example, this concatenation of 3 loops, you first do alpha and beta, and then you do gamma, that will not be the same as doing alpha and then beta, and doing beta and gamma first and then alpha. Of course, in your space X, the image of these loops will be the same. But considering these loops as maps, they're different because of the choice I used in the definition of the product, this 1/2 choice, right? For example, this loop here, how do we obtain it? We first choose 1/2 and we do gamma here, and we choose 1/4 here, and we do alpha beta here, right? That's how you obtain this loop. And in this loop, you split differently, right? You first do alpha in the first half, and then in the second half, you divide it between beta and gamma. So this portion is gamma, beta, and this portion is gamma. So these are 2 different maps, even if the images in X will look the same, right? They will be the same image in X, but they have different speeds, these loops, in some sense, right? So they're not the same. This product is not strictly associative, but you can show, or you can argue, that it's associative up to homotopy. Okay, so there is a higher structure relating these 2 expressions. Moreover, this should be this product. So moreover, this concatenation product is associative up to an infinite family of coherent homotopies. So I want to explain what this means a little bit. So this structure is known as an A-infinity space, and it was introduced by Jim Stasheff in the 60s. So let me describe what the structure consists of. So there are coherent higher homotopies. So you can think of these as continuous maps from n copies of the space we're working with. And this is the Cartesian product of n copies of your space. And these maps, or these homotopies, are parameterized by some polytopes. These kns will be certain polytopes. All of these maps fit together in a particular way. They are compatible. So let me start describing this. By the way, this polytope is called the nth associahedron, okay? And it has an interesting combinatorial structure, which is convenient to define this, this algebraic package in some sense, okay? So for example, when n equals to 2 here, when n equals to 2, what do we have? So when n equals to 2, we have K2 will just be a point, okay? By definition, maybe a point. So when n equals to 2, we will just have, since this is a point, we can just forget about that, right? We will have a map from the loop space cross itself to the loop space, and that will be exactly this concatenation product. That's the first layer of the structure, okay? So now let's go one level up. When n equals to 3, we will define K3 to be the interval. So maybe the interval, okay? So now we will have a map H3, which takes three loops and an interval and a point in the interval, and outputs another loop. Okay. So we should think of this map. So we take 3 loops, alpha, beta, and gamma, let's say, and we should think of this map. This is a 1-parameter family of maps because it's parameterized by this interval. And we think of this map, or we define it to be the homotopy relating this expression, this loop, to that loop. You can construct an explicit homotopy between this loop and this loop, which continuously changes the reparametration used to define this loop to the reparametrization used to define this loop. More precisely, if you want to think about it this way, remember we this was 1/2. Sorry, this was 1/4. So this top interval denotes the loop, this loop, alpha, beta first, and then concatenated with gamma, right? So
you put
here
1/4 where you meant 1/2, right?
Exactly. 1/2 here, right? So this means you do alpha here, you do beta here, and you do gamma here. And this one in the bottom here, you do alpha, you do beta and gamma here. And then you can define a homotopy by just shifting this maybe like that, right? Now this is for every t here, every t, this slice gives me a particular loop, right? In which I apply alpha here, beta here, and gamma here, right? So as I vary t, I get a continuous family of loops interpolating the first loop and the second, right? So this is a homotopy between these 2 loops. So a homotopy for the associativity relation in some sense. So this is what this map H3 gives, right? You start with 3 loops, you start with some t at an interval, and that gives you another loop. So that will give you precisely this red slice in the square corresponding to t. And now the story becomes combinatorially much more interesting because you want to relate different, if you have 4 loops now, if you have 4 loops, maybe I'm going to start using Latin letters, A, B, and C, and D. There are many different ways. Actually, there are 5 ways of putting parentheses around it in a way that makes sense, right? Applying, for example, you can do alpha, A and B, or you can do, and you can multiply that by C and D, or you can first do, I don't know, A, B, and C, and then multiply that by A, and then multiply that by D. And there are 5 ways of making sense of this expression. And now you want to relate all of these 5 ways and the homotopies between each application of the associative law. So you have a pentagon, right? And that pentagon will be K4, the next polytope. So I have a picture here. So this is the number of putting parentheses in this way around the word like this. It's called it's the Catalan number. The Catalan number counts the way of putting parentheses. So that's a interesting fact. And here I have placed an edge for each application of the associative law. Okay, so you think of these as loops, right? You think of these edges as homotopies. And now you extend your construction by defining for every point in the pentagon, you're going to define a loop in such a way that you get a continuous map fitting with this boundary.
Can I ask a question?
Yeah.
Is there a significance to the direction that your arrows are pointing in this, or could they have been undirected?
There's no significance.
Okay.
This is on the, I took this from online. I should put my source, Wikipedia. But right now there's no significance. I will not use any direction of the arrows in what I will say. Yeah. Okay, good. So you can define a continuous map from the pentagon to the loop space. You can actually define a formula if you wish. This was the work of Stashev, such that it coincides with, it agrees with the formula and the boundary for the homotopy interpolating between these 2 loops, right? And you can keep going. And the combinatorics becomes extremely interesting. Let me show you a picture of K5, right? So this is a polytope in which the face, a 3-dimensional polytopes, the faces are squares and pentagons. And the vertices are all ways of putting parentheses around a 5-letter word, okay? The edges connect an application of the associative law. Again, I'm not making use of any direction here, but the edges is a single application of the associative law, okay? And what's the topological construction that, well, you can now, given 5 loops, you can construct a map to the loop space for every point in this solid object, right? In other words, this solid object parameterizes a family of loops, which agrees with certain things that you defined earlier. And let me show you, this is the back of this picture. This is called, these are examples of what's called the associahedron. Okay. So yeah, so let me say here, before I continue, that there is all this structure that the loop space present in the loop space that we forgot when we modded out by homotopy, when we defined the fundamental group, right? Because when you say 2 things are homotopy, all of this information that I have described is collapsed, right? All of these become like equalities. All of these are the same up to homotopy. So I forgot about a lot of information when I modded out by homotopy to define the fundamental group. But still, this is not quite algebraic, because I'm defining this structure on a space, the space of loops. Okay, this is continuous information. So I wanted to make this into algebra. And there's a way of passing from topology to algebra, which is different from taking homotopy groups, okay? And this is the machinery that I will use to pass from this mix of topology and algebra to pure algebra, to just vector spaces or abelian groups with operations between them, this kind of algebra, okay? So this is what I want to explain next. This is a link between topology and algebra, how to make this structure that I just described into algebra. So for any space X, you can define a sequence of abelian groups, which I'm going to call C0, C1, C2, and so on. Maybe these are free abelian groups, and they are defined as follows. So the idea is that you probe your space with simplices, okay? So Cn of X will be the free abelian group generated by this set of continuous maps from a simplex, an n simplex into X, okay? An n simplex, I mean, a zero simplex is just a point, a one simplex is just the interval, a two simplex is a triangle, a three simplex is a tetrahedron. So it's the convex hull of n plus 1 points in R n in R n. I think I messed up. It's the convex hull. Well, you can define it to be the convex hull of, for example, this is the convex hull of 3 points in R2 and so on, right? This is the shape we care about, and you can we assume simplices have their vertices ordered, right? 0, 1. And with these objects, I'm going to probe my spaces. In other words, I'm going to consider this free abelian group generated by the set of simplices inside your space. So these are continuous maps. These can be crazy maps, right? They don't have to be linear in any sense, or they can be any continuous map. This is called the singular. This set is called the set of singular simplices. The word singular just means because there's no restriction in smoothness or linearity. These are just maps that, for example, they can be like that inside your space X, right? The image can look like that. So this is just a big set. And the idea is that I'm going to kind of forget about my space and remember this algebraic structure, okay? I'm going to denote C star of X, the direct sum of all of these abelian groups. So I want to think of this as a graded abelian group. I put all of these together. And now this set becomes with extra algebraic structure, which makes it a chain complex, okay? That extra algebraic structure consists of a sequence of maps between any two consecutive abelian groups, okay? This map is called the boundary map, and it's defined, so the notation here is a little bit cumbersome, but it's defined to be the alternating sum of the faces of a simplex, right? This is what this means. You restrict a simplex sigma to the face obtained by forgetting the ith vertex. That's what that notation means. So let me, a picture is worth a thousand words. So let me just describe it here. So given a, for example, a two simplex in your space, considered as a basis of C2, right? It's a generator in this abelian group. You can this map delta is defined by taking this alternating sum of all the faces of your simplex, right? And this expression lives in the free abelian group C1 of X now, right? It's a formal sum with coefficients, with integer coefficients of singular one simplices. Okay, so that's how you define this boundary map. And you can check this, one of the first exercise in algebraic topology, that it squares to 0. Okay, it's a nilpotent operator. It squares to 0. This structure of a sequence of abelian groups with maps, linear maps between them that squares to 0 is known as a chain complex. And this particular chain complex is called the singular chains on the space X. Okay, it's a now purely algebraic structure. Sequence of abelian groups with linear maps between them. So let me now talk about a little bit of more algebra. So given any chain complex, you can define this another sequence of abelian groups, which forgets a little bit of information, but remembers certain essential aspects. This is called the homology of a chain complex. It's a sequence of abelian groups for every n, denoted by Hn of C. Okay, and it's defined Hn. You look at the spot n, and you take the following quotient of abelian groups. You look at the kernel of one of the maps, and you mod out by the image of the previous one, right? Of course, the image is contained in the kernel because d squared equals 0 of our first claim. And that quotient is defined to be the homology of a chain complex. This is a purely algebraic construction. And the nth homology of a space is defined to be the nth homology of this singular chains complex by definition. Okay. And now our notion of equivalence between chain complexes will be the following. A map of chain complexes will be called a quasi-isomorphism, almost an isomorphism, right? If it induces an isomorphism after passing to these quotients. So it forgets certain information, but retains certain essential aspects that I will be interested in. If this holds, then your map is called a quasi-isomorphism. And I'm going to treat these as if they were actual equivalences, you know, like actual isomorphisms. That's my goal in this algebraic framework. Okay. An example, if you have a homotopy equivalence between spaces, then they induce quasi-isomorphisms between these chain complexes I described attached to each spaces, to any space, right? So how do I pass from all this package of like all of these higher homotopies that I described attached to the space of loops? How do I translate that into algebra? Well, I apply this chains functor. This is the technical jargon that we use. I apply this construction. A functor is a natural construction. I applied that chains construction to this group, to this space, to obtain this sequence of abelian groups. And it turns out that the concatenation product, remember I had this known associative product with all of the higher homotopies and so on. That product induces an algebraic product at this level of chains of this sort. It takes an I chain and a J chain, and it produces an I plus J chain. Okay? And moreover, this product is compatible with this boundary operator that I have, remember, from for any n, I have a boundary operator of this sort. this product is compatible in the sense that it satisfies the Leibniz rule. In other words, alpha star, maybe I should use different letters, because now I'm not talking about loops, I'm talking about elements in this abelian group. So maybe x star y. If I apply d to that, I get well, the Leibniz rule, dx star y plus or minus, there's a sign depending on where x lives here, the degree of the chain, right? dy. So you have that compatibility equation, okay? So from this algebraic package, I obtain now a product on these abelian groups together with this map that squares to 0, which is compatible with that product. But the product is not associative because of the same reason that the product I started with at the level of spaces was not associative. But this leads to a similar construction in the algebraic world called an A-infinity algebra structure. So all of these higher homotopies that I was describing, which were parameterized by these polytopes, give rise to algebraic maps at this level. Okay, so it's a bunch of maps, and all of these satisfy compatibilities between them. The compatibilities come from the fact that these maps were coherent, right? Remember, I said if you move to the boundary in one of these polytopes, it will agree with the maps that you had defined before, and so on. So all of these compatibilities induce algebraic compatibilities. So all of that structure on the loop space induces an algebraic structure, purely algebraic structure. It's known as an A-infinity algebra structure on a chain complex. And then it's purely algebraic. I obtained it from some geometric construction of these loops with some topology, continuous maps, but now I forget about all that and I just remember, I retain this huge algebraic structure with all of its compatibilities. And again, this is called an A-infinity algebra structure. It's obtained from, in this particular case, it was obtained from what we call an A-infinity space, which was this loop space with all the higher coherent homotopies describing the failure of associativity. Right. So I'm running out of time, so maybe let me go to the yeah. So okay, so I'll take 3 more minutes. Is that okay with everyone?
Yeah.
I'm sorry. Yeah. So I want to try to make into a package. I promised I was going to describe the hidden higher structure behind the fundamental group, right? So I want to make this into an algebraic package before finishing. So the algebraic package is the following. So there's even more algebra that I haven't told you about. More algebraic structure on these chains, on this chain complex associated to any space. So there's any this object, remember, this was a sequence of abelian groups with maps between them that square to 0. And this is for any space. And we applied this construction in particular to this particular space, right? That's what we did. But any space, this chain complex associated to any space comes with a natural operation, but now it's a natural 1 to 2 operation. It's kind of the opposite of a product. You know, a product is like a multiplication. It takes 2 things and produces 1. And this algebraic object comes with an operation that takes an element and splits it into a sum of pairs. This is called a coproduct. Okay, so more precisely, a coproduct or this operation will be a map from this abelian group of n chains on X to the direct sum of these tensor products of complementary dimension, right? I plus j equals n. So you look at all ways in which your I plus j can equal n, and you take that direct sum. We denote this for simplicity by the tensor product of two graded abelian groups, or I should say maybe the degree n part of this graded group. Okay. And in this particular case, this operation is defined as follows. So remember, the generators of this group were continuous maps from a simplex, from an n simplex into X. So let's say sigma is a generator. It's a continuous map from, let's say, the two simplex into X. And this map, or this splitting map, is defined by essentially splitting your simplex at all vertices. So let me give you a picture. You take a two simplex in this particular case, and you have the following splittings. You can split at 0. That only gives you 0 and the whole two simplex. You can split at 1, and you're only looking at complementary dimension, right? This is 0, 0 plus 2 equals 2. I have a question. Oh, I think Wilfredo has his microphone on.
So
That's fine. Yeah, no worry. So there's this way of splitting. I was saying there's this way of splitting simplices in this way, right? You split at 0. That means you get the first vertex and the simplex itself. You can split at 1, and then you get this one simplex together with that one simplex, and you can split at 2, and you get the two simplex itself with the last vertex. Okay, and this is a splitting operation. You can extend this by linearity, right? Because these are the generators of these abelian groups, and you get an operation, right, which has these domains and range. This is called a coproduct because it's kind of a dual to a product. And it turns out that this coproduct satisfies certain equations. For example, it satisfies a co-associativity equation, just the dual of the associativity. You can think about what this should mean. And it's compatible with this boundary map that you always have in some way. It satisfies the dual of the Leibniz rule. So you can call it the co-Leibniz rule. You can write formulas if you wish to try to understand what this means. So this is a structure that comes with any space. You can always associate this piece of structure. So now to any space, we have associated this sequence of abelian groups with this boundary map together with this coproduct. Okay, this is called a coalgebra, or a differential graded coalgebra. Co-associative coalgebra, because this turns out to be actually strictly associative, this coproduct. So now what I want to end with, with two comments, and they are the following, now we can apply this to the loop space, right? This extra structure of the coproduct will also be present in the loop space because it's present for any space. And we get this huge algebraic structure. But again, it's purely algebra. It just consists of abelian groups and operations between them. So what I want to end with is that this chain complex obtained by applying the chains to the loop space together with the boundary homomorphism, this boundary map, together with the product induced by concatenation of loops, plus all of its higher homotopies, remember there were higher maps measuring the failure of this product in being associative and not being associative, right? The failure of associativity, together with this structure, this 1-to-2 operation that I just described, encodes what I described, what I called the higher homotopical structure behind, hidden behind the fundamental group. Okay. And let me pass to my final slide, and I will write something here. And the point is that you can do something similar for each pi n, right? You can find all of these hidden algebraic structures in this similar way, in a very similar way, right? And then you can package all of these together, and it turns out that they satisfy relations between them. And you can describe a very nice coherent algebraic structure, which follows this same pattern that I was describing for the fundamental group. And then the final theorem, which it's built on the work of my advisor, Sullivan, together with Quillen, together with Mike Mendel, who's at Indiana University, together with myself. So this is, if I'm just writing all the work that goes into this theorem, all the results that go into it. Myself, Zainalian, my collaborator, Zainalian. The final theorem is that these hidden algebraic structures, of course, I'm writing it in a poetic way, not a mathematically precise statement, behind the pi n's completely determine x up to homotopy equivalence. Okay, so if you have two spaces and these algebraic structures turn out to be equivalent in certain sense, defining the notion of equivalence is part of the content as well. The two algebraic structures are equivalent in certain sense, then it turns out that your spaces were homotopy equivalent. And we can prove this. And it's obtained by refining this higher structure behind these homotopy groups. So I'm going to stop here. I went, yeah, it's 3:25. Thank you.
Thank you, Manuel. Any question or comment?
Someone clicked that, yeah.
Yeah, I guess I have a question.
Yeah.
When I've seen homotopy groups, it always seemed awkward that like it all is about maps from the circle and the sphere and higher spheres and so forth. Like, what's so special about the higher spheres? Why are those chosen? Why are those important? And do people do it with other spaces than spheres?
Yeah, I have a good answer for that. Well, there are several answers for that, but I think the point is that, yeah, so there's a good answer. So any topological space X can be approximated in some sense by gluing disks, like higher dimensional disks, along their boundary spheres. So you can construct any topological space up to notion of up to some notion of equivalence by just taking disks and gluing them along their spheres, and higher dimensional spheres and so on along their boundary. So when you have this decomposition of your space, and this will be up to this notion of equivalence in some sense, this weak notion of equivalence. And it's very natural to study how spheres sit inside these type of spaces, because they are already in some sense built out of spheres. So spheres serve as a building block for spaces up to this notion of equivalence. That's a theorem from the 50s of Whitehead, that you can always approximate a space use gluing disks and spheres and so on. So that's how spheres come. But you can also do the same with other shapes, like simplices as well would work, or cubes probably.
Do you get the same groups, or do you get different groups that way?
You get the same groups. Yeah, you get the same groups. So you can do it as well, but it's contractible spaces what matters. And I guess the disk is a basic example of a two-dimensional contractible space, right? And its boundary is a sphere, right? So yeah. The only thing that matters is that the dimension and that they're contractible. Those are the what matters for these building blocks. Yeah.
Any other question or comment?
Yeah, I'd like to ask something. So you're basically saying that there's more information, that higher structure that does not forget what homotopy groups forget, but then you should be able to retrieve homotopy groups from this higher structure, right? I guess there
Yes, you definitely can. Yeah. There are algebraic constructions that do this. I mean, there's a cheap way of doing it, right? Because in part of this theorem is that given this algebraic structure, you should be able to construct a space from it. That's part of the theorem, because these algebraic structures completely characterize spaces up to homotopy equivalence. So given one of these algebraic structures, you can construct a space, and then you can take their homotopy groups, right?
Kind of like a geometric realization.
Yeah, that's exactly a geometric realization construction.
Okay.
And then that's a cheap way of getting it. But a more interesting question is if you can get them purely algebraically from an algebraic construction that takes these complicated algebraic structures and produces the simpler ones, which are abelian groups, right? Or groups.
Yeah.
That's also possible in some cases, but not completely understood.
Yeah. I was thinking kind of like how you get, like by abelianizing the fundamental group, you get H1.
The homology,
you should be able to kind of forget higher stuff and land in homotopy groups.
Yes, it's possible, but it's a bit more subtle. Yeah.
And I had another question, which is, I mean, homotopy groups, when computable and when computed, are nice in the sense that for pi1 and on, we are dealing with abelian groups, which are well understood, or they have this very nice classification. You can basically just write them out.
Right, but calculating them for a given space is hard.
Yeah. I understand that, but my question is, like, can you write out your construction, your higher structures construction, like just like literally say, this is how it looks like, even for very simple spaces? Like,
it depends on what you mean. This is how it looks like. We can describe generators, what the generators are. Essentially the answer is, I think, no, because this is how it looks like. That phrase would involve some kind of so let me give you a better analogy. When you define the fundamental group, do you know how it looks like? of an arbitrary space? I mean, you can define a group, but computing that group might be a different question, right? Like, you can describe a presentation of the group, but then what, are you happy with that answer, with having a presentation? I mean, we already know that there's no algorithm. This is a theorem in logic or computer science. There's no algorithm that if you input a presentation of a group will tell you if the group is trivial or not. So does a presentation will make you happy? If that is the case, so yes, we can describe things which are similar to presentations, but then computing is a different question, or comparing two things and saying that they're equal, it's a different question, you know?
Okay. Yeah.
Any other question or comment? Well, then, thank you, Manuel, for this beautiful talk. And well, I hope that after we resume our life real time, we can invite you to give a talk.
Of course. Yeah. Thank you, Wilfredo. Yeah, we're close. We're 2 hours away.
Yeah.
Depending on traffic, right?
Well, and that make a difference.
Right. 2 or 4 hours.
Thank you very much.
Thank you all for listening. Yeah.
Thank you for coming, everybody, and well, see you next month probably.
Okay.
Bye-bye.
Thank you.
Bye.
Thank you.